good afternoon. My name's Chris Oldwood, it says on the slide, which is great. And hopefully you're here to listen to me prattle on about monitoring, that kind of stuff for a bit. If you're expecting puns and that kind of thing, then definitely not. Definitely not funny ones, but they're not normally anyway. Save that for the lightning talk. So, definitely no humour, all po-faced, that kind of stuff. Come in, take a seat. So I've been a developer for 25 years or so. Development's my kind of primary role. Mostly kind of in working on distributed systems, back-end stuff, largely in finance, but also kind of in the last sort of few years doing some retail web services, that kind of thing. So just to put into context, the whole monitoring thing that I'm talking about, that's the kind of thing I'm talking about. People are in embedded worlds or other worlds. That's definitely not something I've done and not something I'm covering. It's very much kind of sort of services stuff. So if that isn't what you were hoping I was going to talk about, feel free to slip out at any moment. Nobody else will notice and stuff. But, just set kind of expectations. It's kind of split into sort of 4 parts. We'll do a little bit looking at kind of people type stuff. And then we'll look at monitoring, things we might want to monitor. And then look at kind of how we might kind of achieve that, or perhaps common mistakes, things are done, and then kind of sort of fold in a little bit at the end, a bit more about the kind of keeping the sort of signal to noise ratio up. So in peopleware, I think it's in peopleware, DeMarco and Lister say that pretty much every problem's a people problem. I think that's kind of possibly a little bit harsh. That's often taken to mean that it's certain people problem, and it's definitely kind of not the case. Let's be a little bit more friendly and say that often issues around are really a communication problem. People kind of not quite talking to each other, and that generally causes sort of friction. So this is the kind of, I guess, the stereotypical view of what happens. There's this sort of bunch of people over here, which is generally kind of me and I guess probably you. Do we have any kind of sort of sysadmin-y, opsy type people in who put themselves in the opsy kind of camp, or are we all sort of developy type stuff? Okay, so we're probably all on this side of the room. So this is kind of, how it often works. We sort of sit there and we spend years building a system, and then kind of like we lob it over this wall, and then there's this other bunch of people in another part of the organization that we probably don't know very well, and they have the joyful task of kind of making it run and keeping it running and kind of like dealing with issues. And these people on this side of the fence, or wall even, mixed metaphors there, on this side of the wall, generally don't know an awful lot about what we did and how we designed it. They've just been given some kind of loose hardware stuff to deal with. And so, they're kind of kept a bit in the dark. So I guess it's kind of, is it any wonder they're not always happy with us and kind of like the things that we do, because they're kind of left out. They're not really seen as a sort of a key stakeholder in a system that we're delivering. More hugs for ops people. That seems to be the kind of message these days. We've kind of realized that actually these people are really nice people, and actually if we kind of talk to them and invite them and listen to their needs, then actually maybe things can kind of work better. Maybe we can work together and address stuff, and as a result of that, kind of good things will happen. So there's this whole kind of like sort of DevOpsy culture. Put aside the fact that there's a whole load of other people as well that kind of feature into it, but certainly I definitely feel a little bit closer to to their kind of needs going forwards. Of course, though, as we move to the cloud, the kind of opsy people are sort of now possibly work for a completely different company, and this works well in a kind of an on-premise-y kind of environment, but in a cloud environment, they're sort of a bit more kind of divorced or detached from us. So as a consequence, we might kind of take on more aspects of sort of the monitoring side than perhaps we did before. But generally the kind of sort of area that, or the things that I've worked with, there tend to be a reasonable amount of collaboration, or even in cloud-based stuff, there's still people in the organization who sort of look after some of that kind of, or at least help out with stuff, even if it's just sort of security and some aspects of networking stuff. So definitely. We often talk about mechanical sympathy as us kind of understanding a bit more about how the machinery works. Where's operational sympathy? Us understanding a little bit more about, what they need and what they've done. Quick question. So how many people have had that conversation with their colleagues where they're arguing about the number of log levels that there should be in their log files? Yeah. Oh, good. Yeah. How many is the right level? 5, 6, 7? I mean, I certainly remember having a conversation where we probably spent at least an hour trying to decide what the difference between debug and trace was. I mean, you know, it's fairly kind of pointless. I mean, we even had at one place we had an error, and we had a fatal error. I mean, I pointed out that probably a fatal error was probably the last error in the log file. But apparently we needed a special error level just for that kind of thing. But, you know, these conversations kind of happened. Certainly years ago, I missed the point. I mean, more recently, I think it's been suggested that there are only 3 levels. There are FYI, there's OMG, and there's WTF. But actually, even now, those decisions around kind of the severity things is sort of starting to disappear, because actually it's not a decision that the code can necessarily take about what is an error or necessarily what bad. We should sort of frame things kind of in a slightly different context. We don't really need to worry about that. That's something that we get from analysing the behaviour. So there's these kind of, so, you know, within our kind of our diagnostic kind of data, there's multiple narratives. And this is, as a developer, dealing with kind of log files and stuff, or logging sort of diagnostic data, understanding kind of that really there were at least 2 different things kind of going on. On the one hand, there's kind of like our sort of operations team. They're interested in kind of the holistic view of what they're, you know, how the system's behaving. And obviously they cover things like CPU and specifically kind of hardware resources and stuff. But also they're kind of interested in kind of some other aspects as well that they can kind of help them piece stuff together. But they're generally involving like how things working at possibly a cluster level rather than what's happening at every single kind of down at kind of operation level. So they're kind of looking for some real kind of like big picture kind of stuff, mostly, which they can attach alerting to and that stuff. And then kind of this is us over here. We're the people that possibly might even be oblivious to this stuff until, you know, the people are running around like headless chickens, and then they call a developer in and say, right, but what's actually going on? Because we don't know what's going on inside this black box that you've asked us to look after. So we kind of delve in, and so we're kind of interested possibly in what's happening at each operation or within sort of very fine-grained stuff, trying to find out you know, if there's a common thread, if there's something we can kind of piece together. So we're looking at a little bit more kind of detail. So that's a different view for us. And then finally, this sort of, again, in more recent times, this idea of testing in production, which is a really scary term for business folk, and as always, there's probably better ways of framing it. But really, you know, testing in production is just another form of monitoring. But it's about, you know, our businesses kind of getting more involved in us providing data that they can kind of use, perhaps a system in a slightly different way, such as features. You know, how much use particular features are getting, which is kind of easy to mine in some cases, you know, within kind of web servers based on around URLs, whereas kind of like back-end stuff, it's quite hard to see what's kind of, you know, how those things are being used and what the take-up is. Because funny enough, we very rarely like delete features. So they're kind of like maybe getting a bit more involved in you know, seeing how features kind of play out. So there's these kind of like 3 different sort of things, and they're all could potentially be used in a similar way, but it's how we sort of begin to combine them. So we often, this sort of full stack developer has kind of come up in the last few years, that there's these people that do front end, they do back end, and then they kind of like do databases stuff. And I've never really kind of liked that term. And so I decided I'm going to start calling myself a full pipeline developer. I'm kind of like, I like the more life cycle kind of oriented approach, which says, you know, I'm generally in this codey, testy kind of bit. That's, you know, I'm a T-shaped person. You know, I have depth in that kind of area. But you know what? I want to understand, you know, I want to know a little bit more about, you know, when I get, you know, features that come through an architect level, you know, how's the build pipeline work? How does deployment stuff? How does stuff actually get packaged and put on machines? How do things work in terms of, you know, high availability, if you're trying to do rolling updates and that type of stuff? I mean, this kind of stuff, again, often is something that, you know, an operations team might be involved in, and yet that doesn't kind of seem to feed back to the teams, and yet, you know, it kind of matters. You know, you can't do it without kind of some cooperation. And obviously, once it's kind of in production, you know, I want to know about how this thing's monitored. I want to know, I've built something. I want to know what's happening, you know, day to day, how things are panning out. You know, what the problems are, and even being involved in kind of support. things, which, I mean, nobody really likes sort of being involved in support. I mean, ideally we wouldn't have to, nothing would ever go wrong. But again, having appreciation for those kind of issues, I think is quite important. So I kind of think that those are the things which, I'm particularly kind of more interested in. The term will never catch on, obviously. So, but I guess, to what end? And I think the kind of end is that nobody gets woken up at 2 o'clock in the morning. I certainly don't like being woken up at 2 o'clock in the morning, and I'm sure that nobody likes being woken up. So, part of this sort of ability to understand what's going on helps us kind of deal with things. We should be able to kind of feed back from stuff that's happening in production into the system, so that kind of going forwards it kind of recovers a bit better. So I guess it's kind of this idea of self-healing systems. So there's two feedback loops, I guess, that kind of come from that. There's sort of a kind of a short one where things that perhaps that are happening, which kind of need to be remediated, that can be remediated reasonably quickly, maybe in a slightly kind of crude way. But then there's a much sort of larger arcing path round, which is more if we're listening to kind of what's going on, and rather than just kind of like bashing out some kind of bit of alerting or script that kind of kills things or run around and killing agents and doing stuff, that we kind of feed that back in and go, well, what's actually really going on? How do we kind of feed that back in? Maybe right even back into the architectural level, so that actually the system kind of like be changed kind of more over time to sort itself out. So as a kind of a more concrete example of this, I've recently worked at a retail organisation that was involved in selling tickets, and they had it was kind of like a multi-tenant system. And when I kind of first joined, there was sort of a number of kind of little production incidents that would happen reasonably kind of regularly. They already had some aspect of monitoring that was happening on the database, so they were getting these kind of like low-level events where maybe there was a large number of page latch events, or temp DB space was being kind of consumed. And this kind of like, the pager would go off and people would sort of jump up and then dive in, and people would start running scripts and tools and things, and they'd kind of try and narrow down what's going on, and eventually kind of like, find some way to kind of remediate the problem. And as just kind of, an observer, I was quite interested in this, was that I found that they were kind of generally doing the same things each time. So they would run the same script, the same tool, and then looking back over the kind of Slack commentary, they would kill a certain thing, and it would usually always be some form of long-running report. Now they were using had transactional and reporting stuff all in one database, which is kind of known as a sort of a potential kind of source of problem. And certainly as the organisation has grown and the data volumes has grown, this sort of started to become more and more of an issue. But what I felt was interesting was the fact that they were going through the same manual process, and naturally being a sort of a toolsy kind of automation-y person, to me, like the moment this had happened twice, I'm like, we should automate this. If I've got something that's already firing an alert and saying that this particular event is happening and it's come from the database, and then I know that the first thing this person's going to do is just run this store procedure to look at some data, I should just run that as soon as the alert triggers. And then they look at that, and then actually there's some heuristics that they're probably applying to the data. They're filtering out some things, and then they're probably looking at certain patterns in the data. Well, we should be able to apply the same heuristics in a bit of code. And ultimately, we should then be able to turn that around and cause that to possibly terminate whatever it is that's a long-running, if there's a particularly long-running query or something, we should be able to just make that happen. And that shouldn't be expensive. We have enough examples of what's going on. We should just be able to make that happen. And that's a reasonably cheap thing to have done. And as a consequence, instead of everybody jumping up, because of course, although they were very good at managing incidents and having people in specific roles and making sure that everybody didn't get involved, everybody else in the office was definitely aware that it was going on. People were sort of a bit on tenterhooks, thinking, oh, do I need to get involved in that? And actually, there was an element of trying to stop people getting involved, so you don't end up with everybody trying to run the same procedure to find out what's going on. So, there's in terms of lost time dealing with these little incidents, probably could account for a significant amount of money, probably far more than what it would cost to write a script. So that's that kind of short feedback loop, something that we should be able to kind of look at, help them remediate the stuff. But ultimately, what the operations side of people knew was that it was always the same part of the system that was failing. And to them, it's like, oh, it's this thing again, it's this reporting stuff. And yes, they were aware that there was to move to split the databases up and introduce replication and stuff so that reporting and transaction stuff weren't in the database was a large task. That's not a cheap thing to implement. But I also think to myself, what smaller things can we do? We've got something very quick we can do. Are there some other things that we can do which would just help improve things a little bit more? Can we preempt some of this stuff, or can we, that's kind of things. So for instance, something I was surprised to find was that there was this known sort of area of problem, but they had no statistical data around this stuff because it was a multi-tenant and clients could submit all manner of jobs. There was no statistics about how long these things took to run, how many rows they returned, and that kind of stuff. So the first thing that we did was to introduce some very, very basic metrics around that particular area. At least help gain some insight. And there were some very surprising queries that were run that were returning millions of rows of data, which we're quite sure nobody looked at that PDF, and it's probably been running for ages. So immediately they could go in contact with clients and find out, why are you doing this kind of thing? Give them something to talk about, and maybe find out what's kind of going on at their end. But also, we could kind of feed some of that in. Modern relational databases allow you to get hold of things like statistics, logical reads, physical reads, this kind of information that you can pull back from running a query. You can even get back query plans that tell you kind of the costs. So I started thinking about some of this stuff, knocked up some little bits to try and help maybe capture some of this statistics. Because I could see at least two approaches here. One of those was we would capture some historical data around some of these schedule reports and maybe just kind of like come up with a cost figure that we could associate with them so that we ensure that really expensive queries don't run together, which is something that they hadn't already got. Maybe we serialize like monster ones, that kind of stuff. But then there was sort of other ways. They also had the ability to create ad hoc reports through a user interface, which would be a slightly different problem because these are a bit more dynamic. But technology like SQL Server or Oracle allows you to find an estimated query plan. So for instance, you could kind of run that query and say to SQL Server, hey, what do you think this is going to cost? And it comes back with a nice little bit of, well, not nice, no XML is nice, but it comes back with a piece of XML and you can extract a cost and estimated row sizes. I mean, that kind of information is not very hard, it's a few lines of code, but it allows you to kind of maybe sort of do a dry run of that query. And maybe if it turns out that it thinks it's going to return you millions of rows, you might want to pop a box up to the user and say, are you sure that's what you want to do? So there's potentially a way of preempting, or at least stopping, maybe some of these things happening. There was certainly a case of people would often, it's a bit like F5 syndrome, where they'd submit a report and it wouldn't run quickly, not realizing that, of course, this thing's running, so then they'd submit it again and again. So these kinds of things. So again, from the developer position, trying to think about how we avoid those kind of problems. But that's very much something that would come from our end. And that's a part of that, I guess, is because the operations team can't affect our backlog. So we have to work with them and say, give them examples. But, yeah. Any questions? No? Cool. That's it. So let's move on from kind of people issues to what am I talking about? What sort of things monitoring? I've mentioned that operations people will cover certain aspects of kind of hardware, low-level stuff around CPUs and memory, network cards, networking, that kind of stuff. So what kind of things can we add to them as sort of application developers? So I've kind of put together a little list here with a blanket instrument everything. That's a nice kind of clickbaity kind of title to the slide. But let's be a little bit more realistic here. Instrument everything you can afford to is probably a slightly more pragmatic statement. And what do I mean by afford? So on the one hand, there's kind of affordance in the sense that the act of monitoring something or instrumenting it can obviously cost more than the operation itself. For instance, if you're writing single bytes to a file, logging how much it takes to write every byte is probably going to cost more than it's going to take to write the byte. Don't do that. So there's an element of granularity, ensuring that you don't impact the thing that you're trying to observe, at least too much. But then on the other side of it, there's affordance in the fact that this stuff, monitoring stuff, costs money. Even if you set up your own stack, elk stack, and sets up containers and storage and everything, that's still kind of going to cost money. I was looking the other day at, I think it's Logs.io, 10 gigs worth of monitoring data will set you back, say, a few $100 per month. In comparison to programmer time over the year, that's what, a couple of thousand, a few $1,000s. I think most programmers are pretty expensive in that terms. And if you think about the number of people kind of involved in incidents, even not necessarily directly involved in the incident, but are kind of sitting there in the periphery waiting to get involved, I think it's quite easy to cover that sort of basic cost reasonably easy. As you start to obviously instrument more, though, this is going to cost a bit more, and it's going to cost you a few more thousands. And obviously at the other end of the spectrum, tools that provide better searching of data and reporting and alerting are going to cost you even more. Splunk have this nice bit of marketing fluff that it costs less the more data you put into it. Sounds nice, but still, you have to put an awful lot of data in to get those kind of economies of scale, but by then you're spending a huge amount of money. But maybe for a bigger organization with a lot of microservices and stuff, that kind of thing pays dividends. So there is an element of affordance. Small companies can't afford to stick too much stuff in, but it does cost money to look after the stuff. So there is a balance possibly between things that you might have to factor into it. So let's go, some of the kind of examples here. From thinking about these more from possibly an applications perspective rather than a kind of an Opsy person. So obviously, file I/O, how long it takes to copy files, or how long it takes to read files into memory. It's a nice, obvious operation. Some time back, I was working on a calculation engine that used a Windows file system to store files, which is great in the early days. I mean, Windows is not the best tool for serving up files, but it kind of worked reasonably well to start them off. As they added more nodes into the thing, things started to grind a bit. They were using memory mapped I/O, so it was quite a transparent sort of thing. But what hadn't happened was, although they could see that things were kind of taking a little bit longer, they were reaching the point where reports were sort of missing deadlines, or at least very close to missing deadlines. And trying to investigate at that point was quite late in the day. And it took a lot of effort to try and find out that effectively this poor old Windows service was pretty heavily underload, and effectively the disk queue length was just astronomical as it was trying to struggle with so many boxes, all not the right tool for the job, but it's kind of one of those sort of slow things to catch up. Move the stuff onto a dedicated filer, and lo and behold, everything kind of works quite well. But at the same time, putting other instrumentation data in, so as the volumes start to grow, we get a better idea of how things are kind of happening. So file I/O is definitely other sorts of I/O, network I/O. Obviously, there are low-level things around sort of DNS lookups and stuff. But any requests to any external service that you make, you definitely kind of want to measure that stuff. We had something sat outside of our perimeter once, which had this rather odd behavior. We discovered that whenever it received a 404, it would close the socket. As a consequence, we were in the middle of building a new version of an existing service. So most of our data relied on the fact that 404 would tell us whether it was in the old one or the new one. So most of our sockets were being shut. Effectively, most of the sockets were being shut on every single request, which meant that we were going through the TCP handshake on every request. Worse than that, because everything's encrypted, so now we're going through the TLS handshake on every single request, and every single request was basically taking huge kinds of amounts of time, things that didn't add up. Meanwhile, we're also tuning up sockets kind of on the proxy servers and other stuff, and generally kind of causing mayhem. So, but again, having instrumentation in from the word go, having things and looking at stuff and going, well, those numbers don't make sense. We shouldn't be costing hundreds of milliseconds to make outbound calls to do stuff. So it helps. Memory consumption, I think it's reasonably kind of obvious. Probably more from things where you have, although they would probably monitor things like stateless things like web servers and stuff, if you've got any kind of other processes going on where you might be consuming huge amounts of thing like rendering. We had something where we were rendering reports at one place, which was consuming huge amounts. And actually, that memory consumption turned out to be because this report was requesting millions and millions of rows. But it was not obvious that the reason why this thing's blowing up is because probably somebody's running a query that's requesting too much data. This kind of cause and effect thing. Maybe it's a little bit easier if we'd had a better understanding of the results from the data, rather than trying to look at some resource issue. Computation time. Anybody who's had to deal with a computation that's decided to go sort of O(m) times n rather than being linear, sort of grown over time, dealing with computations that go. We had, where there's a loyalty scheme, people's transaction histories was growing. Somebody had added an algorithm which was ended up doing an iteration over a list and then iterating again, classically. And luckily, it was a canary that pointed this out early, because that was generating a massive history much sooner than a real person would do it. And so we kind of caught it early. But again, having that there telling us that we've suddenly fallen off of a cliff is a good thing to have. Queues. Operations team would measure something like a RabbitMQ queue or a TIBCO queue, that kind of stuff. But we often have internal queues or collections that are used as queues. Potentially those sort of things. Time spent waiting in those queues is quite an interesting thing to measure, because that will give you an indication of where things possibly there are bottlenecks within a system. Because there may be multiple queues and they might be backed up at the front or kind of in the middle to help you balance out kind of computations. Async await is another interesting. A lot of people, have taken on board this kind of notion of asynchronous stuff, particularly sort of in the C# world, where the compiler generates a nice little state machine, and we do a little bit of work, and then we go to sleep, and we do a little work, and then we go to sleep. We kind of end up on the back of some thread pool. Effectively, we know how long we spend kind of doing some actual work, but how much time do we spend in that queue? There's some interesting patterns from design patterns in the early plot books around that came from kind of like the networking people. One of them about fresh work before stale, rather than using fair queues to try and change things. That kind of stuff, I think, is sort of kind of lost as there are these internal queues that perhaps we don't realise are there. And so trying to account for time can be quite interesting. Cache efficiency. Obviously, if you've got a cache, it would help if you knew what your cache rate was. I mean, there are assumptions that your cache is working pretty good. Maybe you've designed it, you've got some idea, but actually, does it continue to work as effectively as once did? I worked on something where we had a cache and a market data service, and the cache had been implemented, just a simple cache using a kind of a dictionary, and some unit tests had been written. So great, this thing all works according to stuff. We plugged it in. Fired some, the thing was just deployed. I mean, what could possibly go wrong? First look at the monitoring data, and every single request ended with a cache miss. Well, that's odd. This cache is definitely appears to be working correctly. So, but unfortunately, it turned out that the service, the WCF service, was set to create a new service object on every single request. So it created a new cache on every single request. Hence, cache miss every single time. I mean, there were other indications, which was the fact that we were reading far more data, but ultimately, those statistics allowed us to see pretty quickly that although the cache worked in theory, we needed to do something else to make it work in practice, put the magic attribute on, check, lo and behold, everything's working. It's great. And then over time, that sort of cache kind of like dropped down as it turned out that more and more data was custom data was being requested, and actually the cache was serving far less purpose than it was back in the early days. But it was important to know that kind of stuff. And goes with that, I guess, pool usage, similar to kind of caches really. If you've got some kind of connection pooling going on, it's useful to know what kind of state you're in. Anybody who's read the Michael Nygaard Release It book, connection pools, particularly database connection pools, are an interesting kind of source of failure. If you are specifically limiting your connection pool, for instance, to ensure that you limit the number of connections and therefore you can fail faster and return, it's important that you know kind of what your capacity is and what your connection pools are kind of sitting at. So anything like that, where you've got that managed resource, it's useful to have that. Query execution times, we've kind of talked about databases, pretty much any database query. I mean, they just that's still a very dark art, isn't it? Kind of like, SQL tuning and queries that, data volumes change, statistics suddenly get interpreted differently, and you get a query plan that's just crazy. So it's useful to kind of know. And feature use, which is, as I mentioned, knowing when maybe features aren't being used anymore, and we can delete some code or turn them off, that kind of thing. So kind of like there are two ends, I guess, for why we kind of want to consume this data. So the first part is this sort of transient stuff, things that kind of just happen. We're not expecting it to kind of happen again, but maybe weird things. In some cases, when things actually fail, that's quite easy, because usually error messages are everywhere and kind of dashboards light up, and that's really nice. What's harder is when things don't quite fail, but maybe they're a little bit ropey, or maybe they're taking a little bit longer than expected, and then it's kind of hard to pinpoint things, because maybe you've got some occasional timeouts or some stuff that's taking longer, and you can't quite piece together what's going on. So having a choice of other pieces of having other metrics around other components to kind of help you sort of decide or help you see what's going on inside kind of might help you work out what things not quite functioning correctly. But that tends to be the thing that we create most dashboards for, is the kind of actually, is things working today as kind of as we would expect? Where I think often things get missed out, though, is when we start to look at the sort of the longer term picture of things. We all have our dashboards, that's great, where everything's working okay today, but has anybody noticed, things that are creeping up, things that once upon a time used to be quite quick, but now taking a little bit longer? There's a kind of I don't know whether it's true, but the story of, the frog, that if you stick a frog in a pan of boiling water, they kind of jump out because, it's boiling water, why wouldn't you? Whereas if you put a frog in cold water and then you turn the temperature on and you heat it up slowly, it kind of is fairly oblivious to the thing. And that's often what we are with kind of monitoring data. It's, request times. Maybe we just measure some averages, and in the background, our dashboards, everything kind of looks okay, and from one day to the next, but we kind of don't notice these little things slowly creeping up. Volumes have changed. Or, in recent times, we suddenly find that, we've deployed new versions of as we're sort of deploying software more frequently, things have changed, third-party packages have changed, even kind of the OS has changed, and all these kind of things have an effect that potentially over time could sort of slowly, sap little bits out of it. We need to keep an eye on it. I was involved in an investigation for a system that they had their dashboards, and I think they were quite proud of the fact that they could see they had a set of rotating dashboards with average times and request times going on. It was involved in retail, and one day there was this things sort of really started to kind of fall apart. They started to get these kind of weird sort of spikes, even in their kind of sort of average times. An investigation kind of ensued, and something that, from an architectural perspective, which was discovered was that the data, which was effectively around kind of loyalty data, was stored in a database, but it wasn't stored using a clustered or an index-organized table where each customer's data was stored with a high locality of reference. They'd gone for a simple heap, which is basically just, keep appending on the end tables, and then they'd added an index on top of it for fast lookup. I mean, that's obvious, yeah, the index stuff. Of course, when the database was quite small, kind of a lot of stuff fitted in RAM, even the number of, things were generally quite close together, the number of pages, but over time, obviously, this database grew bigger and bigger. Some people's histories obviously started to grow longer and longer over the years. But the problem was, the poor old database, I mean, it had a certain amount of memory in it to start off with, and it had been given a little bit more here and there over time. But what had not been noticed was the fact that as the data in the heap was getting larger and larger, the data was, for every customer, spread out further and further. All of a sudden, the number of sort of reads to read any customer history was suddenly going from sort of a few pages to tens of pages as it was spread out. This physical need to read physical pages caused demands on I/O, actually caused huge demands on the SAN. Turned out that the SAN was also used, obviously, by a lot of other things because it's tends to be a shared resource. Another system that I had worked on was experiencing weird stuff, like we were taking 30 seconds to log a message for an operation that took a split second, where there was no other dependencies, which was just seemed entirely random. It took months to get to the bottom of this. But this, shared resource, effectively there was a failure on it. The amount of load that was being pushed on trying to read all these physical pages, the database was putting so much load on it, it was causing other things. The errors, failures were jumping the cracks, causing other systems to kind of misbehave. If they had some kind of basic kind of like historical data, they would have noticed that the outliers had grown massively kind of over time. Or if they had some other tracking around, physical pages, they could have seen this coming a lot sooner. And as a consequence, there was no way to kind of rebuild the data and kind of remediate the issue kind of before Christmas. So long-term data is something we really need to kind of like keep a track on if we kind of understand how our system's growing, both in terms of volume, but also how each delivery changes. New releases of packages often cause very subtle changes in memory footprint, that kind of stuff. So we should keep an eye on that stuff. Cool. Any questions before I carry on? No? So, how do we record this stuff? We're talking about capturing data. Let's look a little bit more about how might be one particular good way to record some data. So let's start with back to the good old log file. Text-based log file. This is great. Staple of many kind of systems. Again, if you kind of read Michael Nybard's book, this is the classic left-hand side here where we're trying to keep that fixed width, and we've got our various log levels here going on, telling us what's going on, threads and times and stuff. The great thing about free format text files, if you're a budding author, is it gives you a blank canvas. You can write wonderful opus, magnum opus of messages. You can, you've got the option to use beautiful language and punctuation and write really good messages. Or maybe if you don't like writing, then actually you can just knock something out. But different people would decide to format numbers in different ways. Some people will put a space between the units. Some people will format dates in one way or dates in another. Some people put a random hash in front of a number because it's an ID, and I don't know, people sort of do that stuff. So as a consequence, trying to parse this in any kind of automated way is hard work. It's almost like a battle of your regular expression skills have to really kind of like, if you exercise them, if you're going to try and capture enough sort of kind of minded messages or similar messages, hoping that they're kind of expressed in a similar way. So, they're nice. They give you a nice narrative. It gives you a nice story, which is, it's not, it's good, but it's not really good for kind of like machine reading and at any particular scale. I mean, maybe AI is the answer here. Maybe machine learning will one day solve this problem. We'll be able to throw stuff like this in and it will make sense of the whole thing in real time. But I guess until that kind of thing happens, maybe we can be a little bit smarter ourselves. I put this sort of extra line at the bottom here. I worked on something where I tried to sort of get into the idea of sort of structured logging. I've been floating around and trying to make something a little bit kind of more rigid. And so we had this special logging level, which was like PRF for performance, which allowed us to at least grep out logs much quicker, or at least identify and parse stuff. If you've used a tool like Microsoft's log parser, which was originally written to parse IIS logs and then expanded to parse a whole load of other logs, where you could write sort of SQL queries against log files. It's a really amazing tool. I mean, it's ancient now, but sort of back in the late 90s, early 2000s, it was a fantastic tool. It's incredibly fast as well. We could mine logs across multiple machines with it. So this was sort of, for me, this was the start of thinking about structured logging. But there was one aspect to it I kind of missed and I didn't kind of got to until later. And that is that often it's not just about when we're sort of doing things at a larger scale and we're not in developer mode, we're not thinking about kind of individual things, we're trying to think about kind of bigger picture stuff. Actually, we need to sort of correlate different aspects of this operation. So this sort of start and finish, fetching and then orders and then kind of like these two things. Basically, really there's kind of like some basic operations that if we could express singularly rather than with multiple lines would take some of the pain out of it. So in years, I guess in more recent times, structured logging has kind of taken on a bit more. People have sort of got into it a little bit more. but I think it has become very synonymous with JSON. People, I think about structured logging as about the rendering of the text messages. And I think they are missing the slightly wider aspect, which is the structure is not the JSON, the structure is the events in the data. And that's the bit that we should kind of think about more. And it's more from a looking at what you want to do and consume the data is where the structure matters, not the bit where you're kind of laying it into either onto a disk file or pushing it into a service. So I tend to talk about aggregatable logging because to me, most of the goal is about providing an operations team with data in a way that they can look at it at a much bigger scale, and particularly events across that might seem disparate. They're not about individual requests, but a much higher. So we often talk about events rather than talking about kind of log messages. So here we can kind of see that really there's kind of two things going on here. One of the things is we're fetching some orders for a customer. So there's this kind of sort of persistence, performance thing that we kind of want to capture. And the second part is we're using a connection pool. This is a resource which is scarce. We want to track because we want to use that as an indicator maybe that something's going on. So these sort of two debug messages, really what we're trying to do is we're trying to talk about the utilizations. We're kind of trying to elevate these pair of messages into something a little bit higher. So that's the way I sort of start to look at this stuff, to try and think of what that one thing is. So what does that kind of look like? So I've tried to stay away from the kind of the JSON kind of format thing, and then realised I've come up with YAML, which is an even worse kind of format. So it's not supposed to be YAML. I was just trying not to do a sort of a JSON thing. Bare minimum, what do we actually need? This event, what time did it occur? Something that describes what it is in a way that's less ambiguous, at least in terms of. Sadly, authors will have to kind of put away their ability to write fiction and long sentences, come up with something more succinct, and then some kind of lovely and some kind of value that kind of goes with it. That's kind of like the simplest thing we can kind of come up with. So here I've sort of represented two basic events, and these two things are effectively this simple sort of tuple of three values. It pretty much provides the minimum that we could input and then rely on to kind of monitor things at a kind of a larger scale. We'll come to, we've just called these things value, but we'll kind of come to that. So, naming. One of the two hardest problems in computer science, along with cache invalidation. And we'll ignore the off by one errors joke. So, what's in a name? Actually, a lot of what I think structured logging about is the structure of this. This thing that describes this kind of operation, to me, is where there's a lot of really good stuff. So I've tended to adopt this idea of it's almost like treating it like namespaces in code, where your namespaces are obviously some big component, some little component, something, sub-library type stuff. Or if you think about kind of URLs, you kind of host and then you kind of drill down. So you kind of like tend to read from left to right. There's some kind of component-y thing, and then eventually we'll end up with some key operation: read, write, load, save, find, look up, kind of, exists, those kind of things. And then kind of on the end of it, we'll stick some kind of a type. And we'll keep the types of data quite simple. So as you can see here, we've got in the sort of database kind of scheme of component, some domain type, operation of read, and then the thing that we're recording is a duration in milliseconds. The world I work in, Bizarre Life, tends to still be milliseconds. I guess microseconds is kind of taken over, but certainly in kind of like web services, I think that's certainly up until recently that's still reasonably high. Or you can represent it as a double, yeah. So the key thing being is that units matter, as we know from some of the NASA, but various space missions where units have been misinterpreted by different people and created some catastrophic failures. So making sure, for instance, that when we're talking about aggregating and we start to write more complex queries that cut across data types, that we are aggregating data in the same thing. If you if you end up accidentally including counts of 1, so all of a sudden everything gets treated as 1 millisecond, that can make your performance look really good, which is great if you're paid for the metric, but actually if it turns out that that's wrong and your performance is taking a nosedive, you basically won't spot it because of course your statistics are high. So we need to, ideally we want to try and keep things consistent across stuff. And then, so when it comes to using the tools, we can start to aggregate stuff by wildcarding aspects of these things. So it's unlikely that at a big level we're interested specifically in how long it takes to read a group of orders. It's more likely that potentially we might want to wildcard the read aspect. So if we're using a tool like Logs.io or Splunk or something, we can make that a star and we can say, hey, what's the time it takes, the average time to read orders from the database? A simple one. Maybe we wildcard orders and read and say, actually, what's the general feel of all database queries across the whole cluster? Is that kind of going up or down? Start to get a picture, start to get a feel for what kind of looks normal. So part of this rigid structure allows us to think about how we're going to aggregate stuff. And generally, it tends to be some aspect around resource types or components or things that we want to do, because these tend to be database or the names of external services that we're going to call into. And then this one here, so that one's about timing, which is obviously a very kind of obvious one. Another one is in occurrences of things. So for instance, what I've used here is I've arbitrarily come up with this idea of a connection pool reuse as a thing I kind of want to measure. It's possibly a better example might have been if it was cache efficiency, you might come up with some sort of a gauge type, which is a type that Prometheus uses, which uses a similar kind of scheme to this. The idea that you can represent efficiency maybe 0 to 1 or in a kind of a percentage and then log that. And obviously you can't count, you can't sum percentages, that wouldn't make any sense, but certainly you can track percentages over time and obviously you can kind of average them out and see whether your efficiencies, cache efficiencies are kind of going up or down. As long as obviously the type allows you to kind of gives you some indication of what you can do with it. So occurrences, for instance. Sometimes, though, when we come back to this notion of what can I afford to do, or what can I afford to instrument, is sometimes this would generate huge amounts of events. So one of the good things about having the value where the default value is 1 is obviously if you log it every time, that's fine. If it turns out that that's actually quite expensive or generating quite a lot, maybe you only log every 5th event, but then obviously you just log an event value of 5. So you don't suddenly break operations monitoring by changing the amount of data that you're logging or changing the format. That stays the same for them. It just happens to be that you've batched up a little bit more data. You could do the same thing potentially with timing information. But that idea that you can bulk up counters obviously don't go too far because your time window kind of grows, but it allows you to kind of reduce some of your logging burden. So that's great. Our operations people are quite happy. We've kind of given them some more information to kind of, we've given them something which is stable. They can rely on maybe the top kind of 3 things, or our basic alerting stuff can be triggered on that. But what happens when things specifically kind of go wrong? What happens when we need to start investigating particular cases of failure, for instance? Where do we attach that extra data? That extra lovely long message that we had, now we want to extend it and put more parameters and stuff in it. Well, we kind of need to keep it, we can still do that, but we kind of need to kind of attach it maybe on the end or put it at the end of the structure. So the good thing about the initial structure is you could even do this as a CSV file. I mean, as long as the first 3 columns satisfy that basic thing, you can start adding other columns if you wanted to write CSV data rather than JSON because you've got some inversion. So, it doesn't have to be that, but we can add some extra information on the end of it. So for instance here, it might be that we need to, it'd be good to capture a customer ID, for instance, as a bit of context, correlation IDs, which I'll mention in a moment, and maybe some additional information about what was kind of returned. This kind of stuff where context around data that's returned is really good for kind of like scaling stuff. I worked at a bank where most of the customers generally had portfolios of tens and kind of hundreds of trades. There was one customer, though, in the bank that was an internal customer that huge amounts of stuff was kind of booked at. And every time that particular customer was dealt with, the time taken to read it was astronomical. But it was because it had like thousands and thousands of trades. Whereas by having that kind of little bit of extra information in the diagnostic context, you could effectively scale the value or in the short term. And then we had to change the metric to maybe be more about, rather than just being a dumb sort of value around how long this thing took, maybe it needs to be represented in a, more of a sort of megabits per second or requests per second or trades per second, or something that would even give you a better idea of take that little bit of kind of noise out. That kind of stuff. And similarly, things like this extra bits of information is kind of useful. If you get say for example, there are a lot of failures, being able to add in an extra little bit of information might turn out that it's always the same customer that throws up this particular error. So we can still do that. We've not given that kind of stuff up, but the idea is that we try not to break what is essentially a published interface, which is how we talk to our monitoring tool, kind of by doing it. So I mentioned correlation IDs. In my head, correlation IDs was called Causality, but that's because I kind of date back to the days of DCOM, which is like kind of 90s stuff where I first started doing some distributed stuff. And in DCOM, they had this notion of causality, or a causality ID, which was when one system called into another, made another DCOM call into another component that called into another component, this kind of ID would get passed along. And the reason why they did it was because if you ended up going to A to B and then to D, and then you ended up coming back into A again, it needed to make sure that the call was part of the same causal chain so that it could let it through, rather than blocking it at proxy. Otherwise, you end up with this sort of kind of deadlock. But that kind of idea of passing through some little piece of information from one system to the other so that you can start to correlate together monitoring and instrumentation data from different systems, is hugely kind of like useful over boundaries. So, for instance, here we have A, which, say in a retail scenario, that may well be a till, and a till might call out into some kind of authorization service and come into a loyalty service and various other pricing services and stuff to kind of do its job. If the same kind of transaction ID, and this is kind of in a sort of businessy kind of transaction ID rather than databasey transaction ID, that ID is passed into the same systems, you can start to correlate things across systems, which is incredibly useful. It's nice if that ID as well actually is sort of kind of semi-human readable. Don't rely on it having any particular format, but if it does, so for instance in the retail thing, having things like the store number and the point of sale number and the terminal or terminal number, some date and time information and stuff, just kind of helps give a little bit more something to an ID when you're staring or trying to diagnose problems, rather than just UUIDs, which are pretty forgettable, aren't they? So basically we want to pass that information around. Now, some transports kind of make this stuff easier. So obviously HTTP, we can put a custom header in, for instance, which is great. If you use AWS, Amazon have a AM trace ID, for instance, that you can use that would be passed through on a load balancer, which kind of helps things. So there are some conventions in different stuff. If you're using message queues, you could put a message queue in the header. Unfortunately, if you use some libraries that kind of like encapsulate talking to message queues, they might be stripped off and you might have to kind of push it into the body and then sort of do some more work, but effectively it can be passed in a header. Or if you're using WCF or DCOM or something, it's a little bit more invasive. You kind of have to distinguish maybe a wire level protocol or slightly different from a sort of a logical one. So you can hide the sort of tunneling of information and then on the other side of the fence kind of inject it in at the other end. But this is particularly useful. Where this is particularly useful is if you're in an organization with a number of different services, and if you can get them to share their logging data with each other, this kind of becomes really powerful, because it means that Team D can look at Team E's information from team E, and they can use the correlation ID to try to tie up what they're seeing at their end with what they're seeing kind of at their end. So effectively, this is more about kind of like thinking more about cross-team kind of collaboration to work stuff out. Okay, and kind of finally on this section, tools unfortunately aren't perfect. We have, although there are tools, as I mentioned, a tool like Splunk has some excellent querying capabilities that allow you to split data up and do huge amounts of process, really quite cool stuff with it. It has this idea of being able to create streams within data, so you can write a query that sort of almost generates an event stream or kind of like a table, which you can then kind of join to another event stream, which is another set of data effectively. So if you have like multiple events, you can kind of use the correlation ID to kind of bring them together, and you get kind of like a little table of data. So you can kind of almost see the set of events maybe for a particular request or a particular correlation ID, and you can see retries. So which is quite powerful. The problem is that you have to, it has built-in limitations. So if you're just querying one stream, that's great. But the moment you start joining streams, performance limits within the tool kind of kick in, and the default, I think, is 50,000 events. So if your leading table has more than kind of 50,000 events, things kind of stop joining up. So you have to be highly selective in your data. It's almost like those of you who programmed, say, databases, Oracle and SQL Server kind of back in the 90s will probably remember that the order that you put your tables in your database query drove the way the table worked, because it didn't have a query optimizer. It was like you were expected to know which were the small tables to make the query run fast. It's almost a harking back to that kind of thing at the moment. So you have to be, highly selective in your data. As a consequence of that, the time window that you can deal with is then quite small, which is, again, for very small transient blips, that's kind of cool. But in terms of longer-term trends, it's much harder to get something out of it. One of the good things about moving to a kind of a more structured logging and getting away from log messages is that effectively you can treat it, because you're passing types internally around rather than kind of plain text messages, you can start to do some programmatic stuff with it. So for instance, you can start to sum up and provide local aggregations. And then these local aggregations can then be fed into the tool, which kind of helps you deal with sort of long-term trends. Potentially, you could even react internally to events like lost connections and stuff like that, so that you can, things like circuit breaker and those kind of patterns, or the leaky bucket counter, which can be used to kind of reactivate stuff. Potentially, you could hang them off of the eventing infrastructure rather than directly off the code. It's another kind of avenue. Cool. Right, how many have time? Motoring through, sorry. So, so the last part really is kind of more about thinking about how this kind of affects, how we kind of feed this stuff back into kind of the design of our system. Thinking here more about, when we detect stuff in production, how do we kind of make things, how do we keep that sort of signal to noise ratio high? Often we start off with stuff, we put some instrumentation in, but of course the world is imperfect. The services we deal with don't quite behave the way that we want them to. They'll feed us with stuff. They don't quite follow protocols, or they do things in weird way, particularly if you do anything to do with HTTP. Then we can really decide how to return errors or what certain things mean. So as a consequence, what you often end up with is you have a dashboard, and your dashboard sort of tells you kind of roughly what's going on, but often there's lots of little bits of noise in there. Things that you kind of investigate, but actually it turns out, oh, it's that thing again where they do X, Y, Z, which is distracting more than anything, particularly when, the place is on fire. That's the last thing you want to do, is keep going down into little rabbit holes. So something we need to do is to keep feeding back into things that we discover, or maybe we need to kind of make more use of the fact that we can deliver software continuously much quicker, and add little bits of diagnostic stuff in, capture a little bit more data, learn a little bit more about the problem, and then kind of move on. So I've got two kind of examples of more concrete examples of this. So one of them was the service where we had 404s with sockets being closed. Before that kind of happened, we noticed that as we sort of started to push this service out, we'd quite often get these sort of 500, HTTP 500 errors. And initially, we started with a kind of like a first-order approximation, which was we generated an client error event, which is basically just to say that we'd made an HTTP request, and basically if it was anything other than 200, we would basically log it, and we'd separated out 400s from 500s. We called 400 client errors and 500s server errors, because we thought we'd probably need to react to them in different ways. 500s we would retie, 400 we would assume, well, so 500s usually it's their fault, 400 it's our fault. So we might need to deal with those in a slightly different way. And as a consequence, we started seeing a number of these kind of 500 errors, so the dashboard becomes quite noisy. So we started to kind of investigate them. So the first thing we did was to improve our diagnostic context. We started to include a few kind of obvious headers. We pushed that out. First thing that came up was interesting was we were requesting a JSON payload, and we were getting back HTML. Thought, that's weird. Because we knew that the service on the other side of the fence, because it's owned by the same company, and we could go and walk over and talk to the other developers, and they go, well, we don't do that. So something between them and us is throwing us HTML despite the fact that we've not asked for it. Okay, let's improve the diagnostic context a little bit further. So we add a little bit of the body in as well. Including untrusted input, not really a nice thing to do. So we kind of tread very carefully, capture the first 100 bytes of the body, stick that in as well. We weren't getting too many errors. Add a little bit in as well, maybe just to only capture, say, 1 in 10, that kind of stuff, which is enough to kind of give us a little bit of a sample to see what's going on. Yeah, you're right, they are giving us a bit of HTML. Weirdly enough, it looks like an error message from something. Turns out we discovered that it was the format of an error message that Akamai sends back, who are a company providing some DDoS protection around the service. And with inside that message, it forms quite a rigid structure. There's a UUID, which is an error code, which if you was to give that to the people who own the service, they could look up in the diagnostic tools for that service and find out what's going on. So we fed that kind of back in, wrote a very crude little parser to say, if we get 500 and it's HTML and it kind of looks a little bit like one of these messages, let's pull the error reference out and we'll put that in a property we'll log that as part of our diagnostic context to bring that out. Then we gave that to the other team and basically said, if you see these things and you want to go and look for them, just help yourself. Here's our logging data, you can see it, kind of go and find it. So they started looking into this, and it turned out they started looking up some of these error references, and it turned out that there was a disparity between idle socket timeouts between a load balancer and some other Akamai service, meaning that one end would suddenly disappear and then the other end would get upset and things would kind of all collapse and then everything would kind of spring back to life. But the point was, we had added a little bit of code into ours to give them and gave them access to that data, so they could kind of solve their end of the problem, and we had better visibility because now anything that came up with that kind of error, we could categorize as not our fault, but we could provide them with something to kind of work on. So that kind of improved kind of error handling within the service. A similar one, or at least a kind of similar example, was another service we dealt with where we'd have an awful lot of these as we sort of went into production and started throwing real customer data through it. Suddenly got a considerable number of 400 errors, which we kind of weren't expecting. And so once again, we kind of add in a little bit of extra diagnostic context, find out that these kind of 400 errors, there's a little JSON body that kind of goes with it. And they look like there's a little error code in there. So we went to talk to the team that kind of provides the service and say, hey, kind of like, what does this thing actually mean? And they said, well, it means that the loyalty card that was used doesn't exist. I was like, well, it does exist, or at least the things in the message. So either somebody's giving us Duff loyalty card data, or maybe this doesn't exist. But it turns out that quite a few of the cards weren't kind of in this other database that this other team were using. So this data was kind of missing. Annoyingly for us, there was kind of quite a large percentage of these things. We hoped that maybe they would go and fix the data, but then they said, well, they weren't really interested in fixing the data. So we're now kind of stuck with the fact that we've got this noise in our instrumentation because it's now harder for us to see when we get a 400 maybe that's a new one. Maybe we have actually done something ridiculous. Maybe we have broken something, the client contract, and we might actually break a real request. But we can't see that because it's buried by all of these other requests. So we went back into the code and made a change so that we would then detect if they send us a return us with a 400 and the body is JSON and it's got this particular error code in it, we then transform that into a different thing, which is kind of an invalid card error, which is great because now all of a sudden our dashboard suddenly looks nice again. The number of real 400 errors was tiny. There was like only 1 or 2, it turned out, and this other thing all gets categorized as this other block of data. So we kind of get a nice visualization, basically on what's happening. But also, they basically had, when they did finally get a chance to actually tackle why these things were missing, they could see how much of a problem they had. We were providing that effectively for them. They could have seen that themselves, but their monitoring wasn't as kind of advanced, or they hadn't made the effort. So they could see from our dashboard how the problem was, and as they started to fix it, they could kind of like see it going down, and ultimately we could kind of turn it off. So, this is all about feeding back in what we're kind of learning to kind of keep things up so that, we can always kind of see the wood for the trees. And I think, that kind of all follows under that. So that's kind of it, really. I don't have a book, but I've got some of the stuff that I kind of speaking about is blog, and some of it's contained in overload articles. The causality stuff I wrote a long time ago. It was my first overload article called Causality Relating Distributed Contexts, which kind of covers some of that. There's some other stuff around, if you're looking for some code, then kind of simple instrumentation techniques. The stuff that I've tended to use is really just really basic stuff, kind of handful of lines of code, using either RAII in C++ or dispose in C# with capturing stuff. It's not rocket science. I'm sure you could find some nice third-party libraries, or you could just write a few lines of code yourself. And also some stuff around improving kind of messages and things. So that's kind of, you'll kind of find that, or if you dig through overload, you'll find that stuff. That's kind of it, really. Cool. Any questions, I guess? Assuming I can actually see anybody. No? Questions? Yes?
What do you do if you experience in post-production, if you get too much logging, what do you do other than just raise the lower log level and get rid of, say, all these budgets? Have you used other techniques in the past to decide what you can remove from code base, or find a more finely granular way of getting rid of too much logging?
I suppose I have seen, sorry, for the purposes of the microphone, the question was about how to deal with huge kind of volumes of logging that's kind of unnecessary. Yes, I think I've dealt with something where there was a calculation engine and a lot of the logging was based around individual requests, and because the developers always work with it on a kind of a per request, per trade kind of basis, they would add all this extra logging in, but then of course when this particular code was hosted inside a server, which chewed through say 1.5 million trades, then effectively it just generates swarms, swarms of data, and they don't see that. So one of the things is certainly to try and help other people be more involved in that kind of process, that kind of whole, you build it, you run it kind of thing. They'll get more of an appreciation of it. Ultimately, you basically need to either cut stuff out, and it's very much a case of, I think, sort of start somewhere and start to chop out bits of information that are less useful, particularly, or maybe even coalescing data. So, for instance, stuff around the connection pool, you could coalesce lines into kind of a single message, and then sort of maybe kind of slowly chip away at that problem, or introduce kind of another layer, which is actually looks like it possibly makes the thing worse, which is what we sort of did with the sort of the performance, which was introduce a level which just said this thing is related to that, and then kind of ignore the other stuff, and then which is more about trying to highlight stuff. So it's almost like adding extra messages that are in a different way, just because then they would be more visible and maybe chop away. But I guess ultimately, just some way you kind of have to kind of just start to remove some cruft and And it's a long and arduous process. I seem to remember having to implement a lot of a bit mask within something that said, when you're running in this like developer little one-off tool, then like dump all the statistic data out. But if you're actually running in the context of this monstrous service, then all those XML errors that nobody ever seems to be paying any attention about in the trade data, just don't bother reporting them because people just aren't reacting to them. And I think that's kind of part of the sort of the different narrative side of it, which is that when you are trying to debug this thing, if you have the ability to replay requests locally, then by all means have that extra information on. But when you are running in the context of some giant batch process that's dealing with ones, turn it off. If nobody is going to make any use of it or any sense of it, then you may as well turn it off. Maybe even go as far as to turn pretty much everything off and actually work out what you need to turn back on, because if you still got it there, but it's just kind of hidden, maybe you can, you can basically eke out what's valuable by just taking everything away and seeing. This is best I can kind of offer, I guess. Cool. Yes, Alistair.
Is it more often a help or a hindrance if the libraries you depend upon do their own logging?
I think it's a hindrance because they will do it possibly in their own way. Quite often, third-party libraries that are perhaps written with a more naive notion of like textual logging kind of doesn't help, because you then have to write some translator into stuff. This idea of not logging, treating things as events, is something that Steve Freeman wrote about 10 years ago, I guess. As he wrote a thing as part of the mock roles. So it's not a new thing, but effectively providing some kind of interface and richer kind of objects. Certainly, if you are writing a library and that library is writing free text, that's harder. So if you are going to provide some kind of logging, maybe you would think of it more in terms of events, emit events, and then somebody can then plug in some kind of listener. They can then either turn that listener into text, by all means provide a toString function or whatever to allow them to render it in a traditional log file. But if they actually want that and can use that event data in a particular way, then basically you have the richer data to work with. So I don't think it's a case of, I suppose that the question is, they should not make a decision on how to render diagnostic data. They should allow the application preferably to do that, I guess, is what I'm saying, if that makes sense. That should be the application's responsibility. But by all means, emit interesting events and provide some way of controlling them. Does that answer your question? Cool. Anything else? Yes? Sorry for the microphone. That was the question was about possible ways of retrofitting or moving to a structured logging when you've kind of got free format logging, I guess, to deal with. Honest answer, I guess, is no. If you have a certain amount of structure with dates and times and threads and stuff, you can get that kind of information out, but unless you can kind of maybe tweak some of your existing logging to make certain aspects clearer, that might help you kind of pick things out. So for instance, we in one case we ended up putting like double brackets around certain numbers and stuff, which would kind of help us work out, picking out free text, some bits of information. Was a sort of a crude way of kind of helping things be more parsable. But ultimately, the sort of the movement was kind of away as soon as possible from those, and we could kind of change the important ones, leave behind some of the crust, but keep the bit that we wanted was the timing information, or the some other kind of information rather than the sort of the bits of text kind of stuff, and we ended up having to sort of kind of change code really. But I don't think there's an easy way of that I can think of. Maybe AI will give us the answer, or some machine learning, but no. But I don't know if anybody else has actually got any successful stories around that. Afraid not. Cool. Anything else? Yes. Excellent. It's not. Well, maybe you can go and join the end of the C++ pub quiz and gate crash and get some free beer or something. It's good. Cool. Good.